Now that you've watched the video on the introduction to rotational kinematics, let's dive into a sample problem. It's just good practice to have your equation sheet of the equations we derived in that video out and beside you as we go through these problems. This sample problem is talking about a flywheel. Not many people know what a flywheel is anymore, but let's just imagine it as a rotating disc, like a CD or a record going around on the record player. Here we see that we have a disk that has an initial angular velocity of 1.2 times 10 to the third revolutions per minute. The disk is being brought to rest over the course of 60 seconds. Find the angular acceleration of the flywheel, the angle through which the flywheel rotates while slowing to a stop, and then finally its initial linear velocity and linear accelerations of a point 20 centimeters from the axis of rotation. Here we see this angular velocity is given to us in revolutions per minute. One revolution is 360 degrees or 2 pi radians. So I'm going to have to go ahead and be doing a conversion at this point in order to solve this problem. I need my units to be in radians per second in order to solve the problems. But we're going to be doing a lot of conversions. Rotations per minute, rotations per hour, revolutions per minute. All of them need to be converted into radians per second. And we may have to convert back depending upon what they're asking for in the problem. Here you see my solution to part A. Part A specifically is asking for the angular acceleration of the flywheel. I look at the information I'm going to give. The omega naught, or omega initial, is my velocity initial, my angular velocity. And I notice the information that's not given to me is my displacement, in this case delta theta. So the equation is chosen omega final equals omega initial plus t, just like in our big four equations. But I have to make sure that my omega initial is in radians per second, and you see my conversion there. Moving on to part B, they're asking for the angle through which the flywheel rotates while slowing to a stop. That cues me to the fact that I'm looking for a displacement, and my displacement now is delta theta, an angular displacement. Angular displacement then allows me to use the first big four equation, 1/2 alpha t squared plus initial velocity times time. 60 seconds as our time. We've just found our angular acceleration, which turns out to be negative. Slowing down, consider our initial velocity positive, slowing to a stop, negative acceleration, and we end up with an answer of 3.78 times 10 to the third radians. I could be asked to convert these radians into degrees or even revolutions if necessary, but if not asked, you'll leave your answers in radians. In part C, they're now asking for linear quantities, the linear velocity, linear acceleration, at the instant it begins to slow down. So I know its initial angular velocity is 126 radians per second. I'm going to be using my connecting equations, the equations that connect angular quantities to my linear quantities. Here, velocity is just r omega to get me 25.2 meters per second. That's the tangential velocity at that radius. A theta is the acceleration that is tangential. Remember, this disk is slowing down. Therefore, its speed is changing. It has a tangential acceleration of negative 0.42 meters per second squared. By multiplying by these radii, I'm introducing the unit of meters. Let's not forget our acentripetal. As long as a disk is spinning, it has a centripetal acceleration. At any given velocity and radius, it will have a centripetal acceleration, in this case, given to us by r equals omega squared. I should probably be more careful here and include that negative that goes along with the radial direction, inward being negative and outward being positive. but it's your universe. You decide which direction is positive or negative.